The journey of steel. Steel, a symbol of strength and resilience, has been the backbone of civilizations for over 4,000 years. Originating in ancient Anatolia and Sri Lanka, steel's journey from raw iron to the backbone of skyscrapers is a testament to human ingenuity. Today it's integral in everything from infrastructure to the utensils we use daily, contributing to a global industry worth billions. So how is it made? The journey of steel begins with its primary raw material, iron ore, extracted from the earth through mining operations. Iron ore is found in abundance in countries like Australia, Brazil, and China. These large, reddish-brown rocks are rich in iron oxides and vary in color from dark gray to deep purple and rusty red. Alongside iron ore, coking coal, a high-carbon fuel essential for steelmaking, is sourced primarily from regions like the Appalachian Mountains in the USA and parts of Australia. Limestone, another vital component, is widely available globally. Iron ore undergoes a process called beneficiation to increase iron content and remove impurities. This involves grinding the ore into a fine powder, followed by magnetic separation and flotation techniques. The powdered ore is then mixed with water and reagents, creating a slurry. Magnetic separators attract magnetic iron particles, effectively separating them from non-magnetic waste. Meanwhile, coking coal undergoes a process called coking to remove impurities and increase carbon content. This is achieved by heating coal in the absence of air in coke ovens, transforming it into coke, a porous, hard, and gray substance. The initial processing of steelmaking starts in a blast furnace, a towering structure often standing over 30 meters tall. Iron ore, coke, and limestone are the key ingredients fed into the furnace. Here, the intense heat of over 2,000 degrees Celsius or 3,600 degrees Fahrenheit triggers a series of chemical reactions. The coke acts as both a fuel and reducing agent, breaking down iron ore into molten iron. The limestone serves as a flux, combining with impurities to form slag, which is lighter and floats on top of the molten iron. In this inferno, the iron ore undergoes a reduction process. Oxygen atoms are stripped away from the iron oxide in the ore, leaving behind liquid iron. This molten iron, also known as pig iron, has a high carbon content, making it brittle and unsuitable for most applications. To refine it further, the pig iron is then transferred to a basic oxygen furnace or an electric arc furnace, depending on the production method. The basic oxygen furnace method introduces pure oxygen into the furnace to further reduce carbon content. The oxygen reacts violently with the carbon, creating carbon monoxide and carbon dioxide gases that escape the molten metal. Alternatively, the electric arc furnace method, primarily used for recycling scrap steel, melts the scrap using high-powered electric arcs. This process also reduces the carbon content and impurities but relies heavily on electrical energy. Both methods allow for precise control over the final composition of the steel, ensuring the desired balance of carbon and other elements like manganese, silicon, and phosphorus. Once the raw iron has been converted to steel with lower carbon content, it's time for the main manufacturing process, which refines the steel into a usable form. This stage is crucial as it determines the physical and chemical properties of the final product. The steel is then subjected to a process known as ladle refining, where further adjustments are made, including deoxidation and desulfurization. This process removes residual elements that could weaken the steel, such as sulfur and oxygen. Temperature control is vital during this stage. The steel must be kept at a consistent temperature, usually around 1,650 degrees Celsius, or 3,000 degrees Fahrenheit, to maintain its molten state and ensure proper mixing of the additives. This is achieved using ladle furnaces or through the injection of gases like argon to stir the molten steel, promoting homogeneity. The next phase involves casting the molten steel. The two primary methods are continuous casting and ingot casting. Continuous casting is the most widely used method due to its efficiency and cost-effectiveness. The molten steel is poured into a water-cooled mold where it solidifies into a slab, bloom, or billet. These semi-finished forms are then sent for further processing. In contrast, ingot casting involves pouring the steel into large molds where it solidifies. These ingots are then reheated and rolled into desired shapes. However, this method is less efficient and more time-consuming compared to continuous casting. After casting, the steel undergoes primary forming processes, including hot rolling, where the steel is passed through large rollers while still hot. This process shapes the steel into various forms like sheets, plates, bars, and rods. The hot rolling process not only shapes the steel but also improves its mechanical properties like toughness and ductility. The steel's surface is also treated during this phase to remove scale, a layer of iron oxide that forms during heating. Scale removal is done using high-pressure water jets or by passing the steel through scale breakers. Cold rolling follows hot rolling for some steel products. This involves further rolling the steel at room temperature to achieve tighter tolerances and better surface finishes. Cold rolling hardens the steel, making it stronger and more resistant to wear and tear. However, it also makes the steel more brittle, which is why some steel types undergo annealing, a heat treatment process where the steel is heated and then slowly cooled to reduce hardness and improve ductility. Coating is another critical part of the steel manufacturing process. Depending on the intended use of the steel, different coatings are applied for added protection. For instance, galvanizing, which involves coating the steel with a layer of zinc, protects against corrosion. Similarly, tin plating is used for steel intended for food packaging, while color coatings are applied for aesthetic purposes in construction materials. Quality control is a continuous process throughout steel manufacturing. Various tests and inspections are performed to ensure the steel meets the required standards and specifications. These include tensile tests to measure strength, hardness tests, and microstructural analysis using electron microscopes. Non-destructive testing methods like ultrasonic and radiographic testing are also employed to detect internal flaws without damaging the product. Towards the end of the main manufacturing process, the steel undergoes finishing operations. These include cutting to specific lengths, surface grinding to achieve the desired texture, and shaping or bending for specific applications. The finished steel products are then subjected to final inspections and quality checks before being approved for shipping. Throughout the manufacturing process, environmental considerations are also taken into account. Steel plants employ various measures to reduce their environmental impact, such as using dust collection systems to minimize air pollution, treating wastewater before discharge, and implementing energy-efficient technologies to reduce greenhouse gas emissions. The adaptability and versatility of steel make it an essential material in numerous industries, from construction and automotive to appliances and packaging. The combination of strength, durability, and recyclability makes steel a material of choice for sustainable development, playing a crucial role in building a greener future. Once the steel has passed all quality checks, it enters the final stage of packaging. This involves bundling and securing steel products like rods, bars, and sheets using heavy-duty straps for safe transportation. For some products, additional protective layers such as waterproof paper or plastic wraps are used to prevent corrosion and damage during transit. The packaged steel is